Hi everyone. Today we're going to be working on question 6 from the Unit 2 review assignment. And this question works on force balance of a pneumatic cylinder. The system shown below has a hydraulic cylinder that's suspended load W, with a suspended load W. The cylinder piston and the rod diameters are 2.5 inches and 0.25 inches respectively. The pressure relief valve setting is 1600 psi. Determine the pressure P2 for a constant cylinder speed if the weight is equal to 575 pounds or if the weight is equal to 0. In other words, the load is removed. So the area we're going to focus on is the cylinder itself, the pneumatic cylinder itself. We're going to do something from statics called the free body diagram. I'll walk you through kind of our simple version. I'll go through it quickly. Then we'll do the force balance on that. One thing I want to note is our pressure relief valve setting is 1600 psi. That pressure relief valve is going to be, that line is going all the way back here. Let's draw this all the way back here, and it's connected to our pressure relief valve, meaning that this is going to open, our pressure relief valve will open anytime we exceed that 1600 psi, meaning that P1 is going to be at 1600 psi. That's going to be our assumption for this problem. So now let's look at the problem statement itself. It says a constant cylinder speed. A constant cylinder speed means there's no acceleration. There's no change in velocity. In other words, no acceleration. From statics, this is an equation we're going to pull from either a physics class or statics. Force equals mass times acceleration. Now, if we have an acceleration equal to 0, then we must not have any force. The force must also be equal to 0. Regardless of what the mass is, anything times 0 is equal to 0. So we know that all of our forces need to balance, and the sum of our forces is going to come to equal 0. So let's draw a little diagram of our cylinder. So we're taking a side view of that piston in there. So first we're going to have a force from our extension force, or the force coming from the P1 side, force due to the pressure P1, working downward. Working upward, we're going to have the force due to pressure P2. That would be our retraction force, or the force trying to encourage our piston to retract. Because there's no acceleration, it is going to be, or it's moving at a constant speed. We don't know which direction it's going to, but I'm going to assume it's holding still just for simplicity. The third force we're going to look at is the weight. That's the attached weight on the end. Two different ways we can write the equation are essentially the same thing, just different physics teachers teach it a little bit differently, or different students, depending on how you learn physics, you may be more familiar with one or the other. Summation of forces is equal to 0, and therefore our forces in the positive direction must equal our forces in the positive direction minus our forces in the negative direction equals 0. Another way of doing it, and this is my preference, is saying that all the forces in the positive direction are equal to all the forces in the negative direction, or if we're working left and right, whatever, opposing directions, right? They're going to balance out, they're going to equal 0. Let's substitute in the values that we have here. So in our first equation, you can see the negative force due to P1 and the negative force from the weight, and then the positive force due to P1. The other version would just be putting the forces in the negative y direction in one side and the forces in the positive y on the other side. Now where we're going to pull in our fluid class is with force equals pressure times area. So now when it comes to, let's just carry over those equations. When it comes to the area that our air pressure is going to be acting on, we have the area of a circle is pi r squared, or pi d squared over 4. The first value we have is the diameter of the piston is 2.5 inches. So if we plug that into the equation, we get the area for 1, or the area for extension, or the area of the piston is equal to 4.909 inches squared. Now the retraction side, the effective, we'll call it the effective area. Effective area is what the air is working on. The effective area for retraction is going to be the piston minus the rod, the piston area minus the rod area. We look at this right here. This is the rod going down. That rod has a circular cross section. So if you slice it, you see a circle with a diameter of 0.25. So we need to subtract that from the piston area that we already calculated. So we have area of retraction, or area 2, the area pressure 2 is hitting, equals pi times 2.5 squared over 4, or your piston area, minus pi times 0.25 squared over 4, or your rod area. That's going to get you a final answer of 4.86 inches squared. We can take those values and go back to our equation. So we want to substitute in for every force due to pressure, pressure times the effective area. So for our P1, we'll have P1 times A1 plus W. I'm going to just go with that balanced equation for now instead of equal to 0. We want to solve for P2. So we're going to take the left side of our equation divided by 4.86 and solve for P2, get a value of 1734.4. So notice all of these values we plugged in. We got our pressure 1 from our problem statement. We got our areas that we calculated. We described those. Our weight was given in pounds, so that's already where we need it, in the type of unit that we need it. So that gets us our final answer of 1734.4 psi. If you were to go about for part B, if the load is removed, we don't have to redo all that work. We already have this equation in this state. Let's just substitute the value for W, change it from 575 to 0, go about solving our problem, and we'll end up with 1616 psi. Thank you for watching, and let me know if you have any questions.